Myself Madhav Jha. I welcome you to CodeChef and let's have a look at this question. The problem is the XOR-OR dilemma and the problem code is OR XOR. Chef has an array A of length n such that AI is equal to I. In one operation, Chef can pick any two elements of the array, delete them from A and append either their bitwise XOR or their bitwise OR to A. Note that after each operation, the length of the array will decrease by 1. We will take an example and see what it means. Let f be the final number obtained after n-1 operations. You are given an integer x and you have to determine if you can get f is equal to x via some sequence of operations. In case it is possible to get f is equal to x, we will print the operations, otherwise we will simply print -1. So let's see how our input actually looks like. Let's say for n is equal to 3, n is 3, our array will be 1, 2 and 3. Here I will start from 1. Let's say we pick these two numbers 1 and 2. We do the operation either OR or XOR and we get another number, that is C. So now our array will get updated to C, 3. So this is what we mean by this line. The array length will decrease by 1. And what it means that in the next iteration that let's say we choose any other two number, we can choose C and 3 because those are the only available. If there were any other else, we can choose them. But we cannot choose 1 and 2 because we have deleted them. Let's see what is the input format. The input format is that the first line of input will contain a single integer t that denotes number of test cases. Then the next line will consist a single line of two spaced integers, those are n and x. The output format is as follows. For each test case, we have to output -1 if it is not possible to achieve x. Otherwise, we have to print n-1 operations. In each line, at first we'll print 1 or 2, denoting logical OR or XOR. And the next we will print the operands, that is x and y. Note that x and y are the elements of the array at the time of applying the operation, as you saw in the example, right? Now, the constraints are that number of test cases range from 1 to 5000, and from 2 to 2 raised to 15, and x will range from 1 to 2 raised to 16 minus 1. The sum of n all over test case won't exceed 2 raised to 5. Let's understand the operations of OR and XOR. So let's first understand how OR operates. So for OR, let's say we have two operands, right? We have A and B. What OR does is, if any one of them, let's say either A or B, if any one of them is actually set, right? If they are 1, our answer A or B would be 1. If both of them are 0, we have 0. Now for XOR, what we do is, if both the bits, that is A and B, are operands, if both are same, our answer is 0. If both of them are different, our answer is 1. As you can see, when A is 0 and B is 1, we have 1. But if both are same, that is either 0, 0 or 1, 1, our XOR value is actually 0. Now let's see how we are going to use this technique or the properties to get our answer. So let's do that by taking actually an example, right? Let's take an example, the same one of n equal to 5 and our x equal to 3. So let's first see the binary representation. So if you do not know, it is 2 raised to 0, 2 raised to 1, 2 raised to 2, and 2 raised to 3. So they represent 1, 2, 4, and 8. So to represent 5, we will write 0, 1, 0, 1. Now as you can see, the maximum bits that is needed to represent n, that is 5, is actually just 3. So what we'll do is, we'll write all other numbers, let's say 1 to 5, in only 3 bits, not 4. So let me write them for you. So we have 0, 0, 1, this is for 1, this is 2, this is 3, this is 4, and at the end we have 5. If you have doubt like how they add up to the number that that I'm saying, you can just manually check them. So we have 1, 2, 3, 4, and 5. Now our x is 3 and its binary is 0, 1, 1. So you will observe that if you do XOR of all this number, right? If you perform XOR with all the number, it will be a mess, right? Because we have to perform for these, then these, then these. So rather than doing that, let's see what happens if you do OR. So if you do OR of them, we can be sure that if even one bit in this line is 1, we'll get our answer as 1. We get 1 here, we get 1 here, and we get 1 here. So now what we want is, since we know that we will get 1 if we do XOR of all the numbers, let's find those numbers that we do not want. What I mean is, in this set we have 1, 2 and 4, right? And this is 3. So the bits that we do not desire in our answer is just this bit, right? So let's form two set. One with all the numbers, right? So 1, 2, 3, 4 and 5. And the other one with all the numbers that we actually do not want. So we'll start from the last bit. Do we want this bit? Yes, we do. Do we want 2? We do. Do we want this bit that is third bit? Well, we do not. So what is this number? This is 4, right? So we remove them from here, add it for another set. Now remove this from here. Now perform OR. If you perform OR, even if one bit is 1, we get 1 here, the same here, and the same here. Now you can say this is kind of our superset, right? Superset of all the bits that we actually want in our X, right? In our X, we want this bit. Now, are there some bits that we do not want? Yes, there are. So what we do? We have another set, right, of all those bit numbers that we do not want, right? So we'll do XOR of all of them. But since there is only one number, that is 4, we'll not assume that. So we have 4, we write the 4, right? So it is 1, 0 and 0. And now we perform XOR. Here we performed OR, right? So we took all those numbers. Here we perform XOR to remove all those bits that we do not want. So for this, as both of them are different, we get 1. Both are different, we get 1. Both are same, we get 0. And this is actually 3, right? This was one example, right? Let's take another one. Let's take an example. Let's say our n is actually 4 and our x is actually 2. Now, this particular example will actually give us -1. Let's discuss why. Again, we have 4, right? So how do we represent 4? So 4 we get, okay, for 0, we have 2 raised to 0, 2 raised to 1, and 2 raised to 4. This is 1, 2 and 4. So at max we are going to require 3 bits. So we write 1, 0, 0, 1, we write 2, we write 3 and we write 4, right? This is 1, 2, 3 and 4. So let's make our set 1, that is 1, 2, 3 and 4. This is another set. So let's see what are the numbers that our x actually do not want. So our x is 2, that is represented as 0, 1, 0. So do you require the first bit? No. What is this number? This is 1. So we add 1 here. Do you require the second bit? Yes. Leave it alone. Do you require the third bit? No. What is this? This is 4, as you can see from here. We write 4 here. We remove this. Let's do OR. So no 1. We remove 3. Let's do the OR. So we get 0, 1, 1. Now let's do OR of these numbers. So we have 1 and we have 4. We get 1, 0, 1. This is 5, right? 1, 0, 1. Now we will perform XOR. When we do so, you will see that this will get 1. No, this will get, yes, this will get 1. This will get 1. And this will get 0. You will see what happens is that this is not 2, right? This is actually 3. So why does this fail? It fails because n is actually a power of 2, right? This is an exact power of 2. And the same goes for x. Now, in this situation, there is no way that we can get our answer as x. So this is one of the conditions that we will check to make sure if our answer is -1 or not. Let's see what are the other cases, right? So cases for which the answer is -1. The first one is that if n is a power of 2, and x is also a power of 2, and if both of them do not have any common bit, right? So in this case, if our x was 4, well, we can get that, right? We can simply get 4. But if that's not the case, our answer will be -1. The another scenario is if our x is actually greater than a max number. Now, what is this max number? Let's understand. So as I told you, the max bit that we require to represent 4 is actually 3. So what is the max number that you can get with bits 3? So you can get 1, 1 and 1. Well, what is this number? This is 4, 2 and 1. 4 plus 2, 8, 8 plus 1, 9. Right? So if our x is actually greater than or equal to the next bit, whatever that is, this is the maximum that we can get, right? 4 to 6 plus 1, that is 7, right? And this one is 8. So if our x is actually greater than or equal to 8, we'll say that our answer is -1. And the last scenario is that if our n is equal to 2 and x is anything, right? If it's 1, 2 or 3, let's see which one will work. So if we have 1, so to represent 2 you only need 2 bits, right? 1 and 0, but this is 1. If you do OR, you get 3. If you do XOR, you get 0. Now as we have seen in the constraint, x cannot be 0, it starts from 1. Our only possible answer is 3. So this is one scenario. If n is 2 and x is not equal to 3, we will say that our answer is actually going to -1, right? So let's just summarize. So what we do is, whatever our x is, we write them in the bit format. We check n and we find what is the maximum number of bit that is required to represent n. Then we find the maximum number, right? This is the maximum number, that is whatever the number of bit is. So if the number of bit is 3, we will set the 4th bit, right? This is the number that x cannot be, right? To find the maximum number, if x is, let's say, less than or equal, if x is greater than or equal to maximum, it will give -1. And so what do we do? The next thing is we find all the bits that we do not want. So we make a set of all the numbers 1 till 5. We find all those bits that we do not want. We remove them from the first set and add it in the second set. We do XOR of the first set. Now it might be that the bits that we do not want might have actually come in this OR, right? Because if any bit is set, OR is set, as we saw from the properties. So we do an XOR with all the numbers of OR, that the bits that we actually do not want. So all the numbers here, the bits that we do not want, are in set 2. So with the number that we got by ORing numbers in set 1, let's say that is S1, and all the numbers that were present in set 2, we XOR them and we OR them and get the number S2. Now with S1 and S2, we do the XOR to remove all those unwanted bits and we get our answer. So this is how we get our answer, and these are the edge cases where we get -1. If n is a power of 2, x is a power of 2, and if both of them are not same, we simply say the answer is -1. If our x is greater than or equal to maximum, the answer is -1. And this one, a particular edge case, that if n is equal to 2, the x has to be equal to 3, because it cannot be 0 from constraints. It cannot be 1 or 2, it has to be 3. I hope you understood the problem and the approach to solve it. In case you still have any doubt, you can ask them to our doubt solvers. Let me give you a tour on how you can do so. Move to practice problem section. Once you are there, choose a problem that you want to solve. Let's say you got stuck on this particular problem, that is bidding. Just open the problem and here you can go to ask a doubt. Then in the bottom left corner, you will see a widget that says ask a doubt. Just click on it. You can say, hey, start a new chat. Once you are there, you can type whichever question that you have. So let's say we want to ask, what are constraints? Right. Just click enter. And one of our doubt solvers will definitely solve your doubt instantly. So whenever you're stuck on a question, that is, you are stuck on a TLE or are not able to get an AC, feel free to ask your doubts to our doubt solvers and you will definitely get an answer. Let's check out the C++ code. Just ignore this template. I'm using this template to take input from the input file and output in this file. So I take test case as input, I run the while loop until it is 0, and in the while loop I run the function solve. In solve function, I'm getting two inputs, that is n and x, as given in our input format. Then I take a long of our maximum, right? The number that we talked about. I loop from 20 to 0. So why I'm looping is, so if you go and do like a 2 raised to 20, it's end up something like a million, right? And since we know that the max it is 2 raised to 15, so we do not have to worry about that. Now I'm checking, let's say our n is 5, right? As remember, if our n is 5, how it will be represented? It will be 1, 0 and 1. So I'm checking all those bits and I'm checking the last bit from left side. If it is 1, we apply it to maximum. So what we're doing is we are shifting, right? So we have 1. If we shift it once, it is 1. If we shift it twice, it becomes 2. If we do it thrice, it becomes 4, and so on and so forth. So we are doing that, and we find the leftmost number, the leftmost bit which is set. We are finding it by doing it and, right? So if we have 5, we do our and when we reach this number, right, after shifting it twice, when we shift it twice, we find that, hey, if we perform the on and if we perform the and, the both bit are same, we get our answer as positive. If that's the case, we'll make our max number as move 1 once more, right? So it will move just one more time and end up becoming 8. So as you saw, the max we can reach is 7. So maximum, if x is greater than or equal to maximum, we fail it, right? And these are the conditions that we have set as research in this approach. If it is n is equal to 2 and x is not 3, if x is greater than max, then it is -1. And the scenario when n into n minus 1, that we are checking if n is a power of 2, then if that's the case, and x and n, if the bits do not coincide, if that's the case, we do -1. Now we move on. If answer is 2, this is the answer 112. We do not have to do anything else. As you know, the answer is going to be only 3. That's the only possible answer. Then we make 2 sets. We make the first set, insert all the number in them. Then we make another set, but currently it is empty, right? We check all the bits in we check all the bits in x, right? We are checking it in x. If it is 0, right? As you saw, if the and is 0, that both of the bits are not same, we delete it from our set 1 and we add it to set t, our set 2. Once that is done, we make one num, that is OR of all the numbers that are in set 1. We do that. Then we find OR of all the numbers that we do not want, all the bits that we do not want. We do XOR of that. And once we are done, we print OR for all those numbers, and at the end we print XOR for num and our complement. So now let's check for our example that we saw. So we saw 5 and 3, right? So we saw 5 and 3, and we saw 8 and 4, whose answer is to be -1. So let's just run this and see what is our answer. And this is our answer. We do first OR with all those numbers, and at the end we do an XOR. And for 8 and 4, the answer is -1. Let's move to Python code. The Python code is pretty much similar, right? We take t test cases, we take the input, we run the while loop. We take input for n and x, we find the maximum number, we apply all the edge cases, right? 1, 2 and 3. If it is a special case, the edge case of 2, we print the answer. We form our set 1, we form our set 2. We find OR of all the numbers in set 1 with this, and at the end we find all the the OR of all the numbers that are in set 2. And once that is done, at the end we simply print XOR of the number that we got from set 1 by ORing them, and the number that we get from ORing all the numbers in set 2, that is num and com. We do the XOR and we simply print them. I hope you understood the problem, the approach, and both the code C++ and XOR. I'll see you in another video.